Okay, so medical isotopes. I'm going to just share my screen a minute and show you the teacher's notes for this. Okay, so right at the end here, so there's all this stuff about X-rays, but right at the end, there's radionuclide imaging and therapy. So this is the part of the course if you're doing the medical physics option for AQA. I'm going to do a Control F and then put in isotope. And let's see if we can find the isotopes. Right, so section 6.4, nuclear and particle physics. Isotopes are there. You can see it comes up 4 times. There it is in the activity bit in radioactive decay. And if we step through, we've got the nuclear atom and keep going. Decay constant, keep going. Oh, half-life of an isotope. Well, where's the stuff on nuclear fission and fusion? Again, I looked this up and no, there it is, medical imaging. Okay, so medical imaging, there's quite a lot on X-rays, which we're not going to cover today. But then we've got these diagnostic methods in medicine. So this is AQA A, this specification, and you can see there's medical tracers. There's the technetium-99m, which is the metastable state of technetium, which I've already mentioned once. Fluorine-18, that is used in PET scanners. Then there's the gamma camera for detecting gamma rays. So the fluorine-18, and there we go, this positron emission tomography, that's the PET scanner. So you can see that it comes in to the diagnostic methods in medicine bit of the AQA A. So it's AQA, medical option, and AQA A. Right, okay, so I am going to stop sharing this and pull up a whiteboard, and we're going to just have a quick look at 1 or 2 things about medical isotopes. So, okay, so if you remember from the AQA A thing, there's the technetium-99, which is TC, and then this metastable state, and it actually produces 2 different gamma ray frequencies or wavelengths, gamma rays, okay, and those are effectively pure gamma rays because it's in this metastable state. So we've got a proton in a high energy level within the nucleus, and it drops from a high energy level to a lower energy level, exactly like electrons in the energy levels outside the nucleus. And in the process of doing that, you get a photon of light. It's much more massive particle, the proton, and so the energy of the photon that's produced is much, much bigger, and so it's a gamma ray. So they're always gamma rays, but they do have different frequencies, and it just so happens, I mean, we're still using this Einstein's equation. E, the energy of the photon, is h, Planck's constant, times f, the frequency, and it just so happens that the gamma rays that are produced by technetium happen to be suitable for detection by a gamma camera. Okay, so the gamma rays are suitable for detection by a gamma camera. Okay, I need to say one more thing, and that is that the technetium is made from a molybdenum technetium generator. So you use molybdenum to, it decays into technetium. The technetium stays in its metastable state. It's got a half-life of about 6 hours, which is just exactly the right sort of length of time. You can purify the technetium. You've then got 6 hours to use it. You can focus it. You can do all sorts of things with it. Use it to treat well, radiography. It's radiology, radiography. Oh, I'm not quite sure which it is. Using gamma radiation in order to kill cells, basically. So the cells that you want to kill are the ones that are cancerous, the tumor cells. So you focus them in on that, and you can use it to kill cells. Of course, this is not the only way that you can treat people with medical isotopes, and we'll come to one or two of the others later. But we've got this molybdenum technetium generator. The technetium stays in this metastable state. It produces pure gamma rays. The gamma rays are suitable for detection by cameras. It's got a very good half-life. It's all great. So now the next thing then I need to talk about then is detecting the gamma rays. Okay, so detecting gamma rays, and this is not necessarily as easy as you might think. There's a thing called a gamma camera, okay, and you do need to know what a gamma camera looks like. Well, not so much what it looks like, but how it works. Okay, so a gamma camera. I suppose that I ought not to keep writing it. I ought to write this, gamma camera. Okay. And what I'd like to do is pull in a couple of pictures, and let's go to here. Right, so I've got 3 pictures. So there's this one, which is a picture of a modern gamma. Come on. I can't move it. I can't move it. There we go. Of a modern camera, and you can see it's attached to a bed, and there's a machine, computer controlling it, and you can see that this whole thing will rotate, so you can take pictures from any angle. So this is a nice modern device, and I want to also upload. Yes, let me pull that one in. So this is what it actually looks like, sort of in schematic. Oh, I made that a bit too big, haven't I? Okay, so here this is the patient, and what you're looking at is a cross section of the patient, for example. So presumably those 2 sort of greyish beige blobs are kidneys or something, I don't know. Anyway, gamma rays are being produced from various structures inside the person. But can you see that the path that the gamma rays take are given by these sort of slightly pinkish lines? And of course, they're electromagnetic waves, so they travel in straight lines. And there is a thing, a part of the gamma camera, which is called the collimator. So the collimator is that stripy bit at the bottom, which is made from lead. So effectively, it's lead tubes. And the reason they've got that is because, I don't know if you can see, but the vertical gamma rays are able to travel down. They're effectively like straws. And because they're lined up with, as if you were looking through the straw, the gamma ray can go from the patient right the way through to the crystal that's on the other side of the collimator. But all the rays that are not lined up, they get absorbed by the lead of the collimator. So what it means is that only the gamma rays that happen to be lined up with the collimator get through to the detector, which means that where they hit the detector, that's the equivalent of where they were produced in the patient. And what it means is that you can then use the crystal to generate light. So the gamma ray hits the crystal, the crystal gives a little flash of light in the right place, and then the light is guided using the light guide to an array of photomultiplier tubes. And that it looks like there's just a row, but actually it's a bank. So there's row upon row upon row. And the PM tube, they're photomultiplier tubes, they amplify the light. And so what you get out is an amplified signal. So you get a tiny weeny little flash, it's amplified so that you can see it and it's detected. And then can you see there's an amp stroke ADC? Well, that's an amplifier stroke analog to digital converter. And that then sends a signal to the computer, which can turn it into a picture. So only the gamma rays that are lined up with the collimator get through. So only those parts of the crystal give off a little flash of light, and only the photomultiplier tubes that happen to be lined up with those will amplify the signal. So you end up with an image that is of where the gamma rays hit the crystal, which is of where the gamma rays were produced in the patient. So you end up with an image that works. So this is how a gamma camera works. So it's not your regular lenses. You can't focus gamma rays. We haven't got any way of doing that. Can't do it magnetically or electrically because electromagnetic waves, gamma rays, are uncharged. So you can't force them to change direction like that. So the collimator is the only way of figuring out the source where they were. You can't make an image the normal way with lenses. So this is how a gamma camera works. And so we've got a collimator. The crystal is what's called a scintillator, spelled SCINTILLATOR, a scintillator. Scintillation is where an event happens and it causes a little flash of light to be produced. So the sodium iodide crystal is a scintillator. And interestingly, scintillation is how cosmic rays are detected as well. But anyway, so we've got a collimator, which is these tubes that allow only the light, the gamma rays that are lined up with it through. A scintillator, which produces a little light flash. The photomultiplier tube, which amplifies that signal. Then you've got an analog to digital converter, which sends it to computer, and you can generate a picture. And of course, gamma rays will go through people. And so you can see any part of a person. X-rays get absorbed by bones. Gamma rays do a bit, but not much. And so you can see inside a person. So it's an extra way of diagnosing. It gives you different information to ultrasound, gives you different information to X-ray, gives you different information to a CT scan or an MRI scan. And this a gamma camera forms part of a PET scanner. Okay, now a PET scanner is basically positron emission tomography. The positron is produced by the fluorine 18, and fluorine 18, like I say, produces beta plus positrons, which of course then annihilate with any electrons they happen to come across, which they come across really quickly because the whole world is swimming in electrons. And as soon as a positron is produced, it annihilates and it produces, remember that this is annihilation, we get 2 gamma photons. And they go in opposite directions. They have to go in opposite directions because momentum needs to be conserved. And so you are detecting on opposite sides of the patient. And from the time that those gamma those gamma particles arrive, you can tell where they came from. And that's how a PET scanner works. So you're looking at the very, very small difference in arrival time. So is the collimator polarizing the rays? No. No, Harry, it doesn't polarize the rays. It only detects the rays that happen to be lined up so that they go down the tubes. And you can see the ones that are going at an angle can't get through. And that's all they're doing. So that's what a collimation is, where you make everything line up in one sort of tube. Yeah, so that's collimation. So so that's a gamma camera, and I've sort of hand wavingly told you a little bit about a PET scanner. So if you want to apply intense radiation to a very small part of somebody's body, where a tumor is, for example, then you would package your radiation, your radioactive source, in such a way that it will be shining, as it were, its radiation in the right direction. And nearly always, radioactive isotopes that are placed inside the body, they are beta emitters. I hope that you realize that gamma emitters would just go straight through the packaging and emerge from the person's body and not really irradiate the bit that you wanted to be irradiated. And alpha emitters would only irradiate the immediate, absolutely just right next to its surroundings. It wouldn't penetrate any distance into the tumor. So beta emitters are the sort of radioactive isotopes that you need to treat tumors this way. A friend of mine had a cancer in her eye, and she had to have a radioactive isotope treatment. They placed it in her eye and they pointed it away from her brain. So they put it behind her eye, and so they shone it effectively out of her eye socket. I mean, her eyeball was there, but they wouldn't then let anybody go in to see her. So you could talk to her over an iPad, and there was leaded glass, so you could look in to see her in her room, but people weren't allowed to go and visit because she was basically radiating out wherever she looked, which was awful. But they saved her sight, so they didn't end up having to take her eye out, which was amazing. So beta emitter. So, and it was a beta emitter that they put behind her eye, a little package with a leaded back, some material that wouldn't let the beta radiation through back towards her brain, but it was allowed to shine on her tumor. So beta emitters are often used when you want to treat tumors and you're placing radioactive isotopes inside the body. And when you do that, then there are multiple different half-lives that you need to know about. So there is the physical half-life. This half-life is the one that we are used to. So this is the one that we would talk about when as a physicist, you talk about the half-life of an isotope. So that's this half-life. It's given the symbol TP, and it's the time for half the nuclei in a sample to decay. Okay, so it's the time for half the nuclei in a sample to decay. So it's exactly what we mean when we normally talk about half-life. Okay, so now then there is something called the biological half-life. And that is TB for biological. And this is the time it takes for half of a radioactive sample to be excreted. Okay, so the time for half of a radioactive sample So the human body is quite good at getting rid of things that it doesn't like. And so this is if it's able, if say somebody was had an isotope injected into their blood, it might be cleaned out by the kidneys, and then you would urinate it out. So this is the time it takes for half of the radioactive sample to be excreted. And then there is the effective half-life. And this is called TE for effective, and there's a link between the three. So 1 over TE is equal to 1 over TP, TP, not that it matters actually, plus 1 over TB. Okay, so and that's the definition then of the effective half-life. So you can see that we've got this added complication about of the fact that biological systems have this tendency to clean themselves up. So basically it's not a closed system. The physical half-life is if it were a closed system. Okay, so so now you know about that. So now I'm going to talk about these radioactive implants. And the two that are named that I can find anywhere are iridium, and the isotope that they are interested in is 192, and this one has a half-life of 74 days. Okay, so this is T a half is 74 days. So it's got a long enough half-life that it's not going to drop hugely quickly, but you could leave it implanted for weeks at a time and have it have a slow but sure effect on the whatever it is you're using it to irradiate. There is another isotope which is used as a radioactive implant, and also beginning with I, is iodine. And iodine 131 is the radioactive isotope of iodine, and that has a T a half of only 8 days. So if you were to use this one, obviously you would have to have it would be a really short-term thing. But can you see the difference between 8 days and the 6 hours for the technetium? Okay, so the 6 hours is like one event, whereas the 8 days is enough to have an effect. Okay, and the other isotope that you need to know about, it's not an implant. Well, I think they do inject it. It's fluorine. This is fluorine 18. Okay, this is used in the PET scanner. And this is a beta plus emitter, whereas both of these are beta minus. And the other one, of course, and isotopes I'm going to put. And the other one that comes up is the technetium. I suppose actually, to be consistent, I should write it out, shouldn't I? '99, and it's the metastable one. I actually don't know what the half-life of the fluorine 18 is. And this is a gamma emitter. Right, and that is basically it from the point of view of medical isotopes. There is one other thing that I wanted to mention today before we go and have a little look at some questions, and that is the OCR A, O and B have they call them PAG, practical assessed something or others. I can't remember. Anyway, they're practicals, and the number 7 is Oh, what? Okay, I'll come to metastable state in just a second, Harry. So there is this practical PAG7. It's a practical, and it's using something called protactinium, which is a liquid source, and it's kept in a sealed, well, it's a double chamber sealed bottle. Okay, a double chamber sealed bottle. And what you do is you shake it up. The protactinium, some of it dissolves in the liquid, which if you turn it up the right way, the liquid floats to the top, and the radiation can come out. The bottom end is all sealed in lead. So you can use this to do a proper half-life practical. So the small quantity of protactinium that is dissolved in the liquid decays over time, and you can detect that using a Geiger counter. And so this is a proper half-life practical. So it's not a model of a half-life. This is a real half-life practical. So real half-life practical. And it is one of the required practicals for OCR. Right. Metastable, right? So Harry, you were obviously not here last time when I talked about technetium, which wasn't last time, but the time before, or might even have been the time before that. Okay, so inside the nucleus, there are energy levels that are like the energy levels outside the nucleus. So this is the nucleus, and we've got energy levels, and they get closer together, don't they? And the electrons can fall down and move up. And if an electron moves up, that requires energy. And when it falls down, energy comes out in the form of a wave, a photon. E is HF. And that energy is the energy difference between those two energy levels. And we talk about the energy levels in our atoms, and we draw them as straight lines. And hydrogen's got it's minus 13.6 electron volts up to 0, and so on. These are the energy levels, and they are quantized, and they are outside the nucleus. In exactly the same way as that, Harry, inside the nucleus there are energy levels for the protons. And immediately after a radioactive event, so a decay of some sort, so for example a neutron turns into a proton, you end up with a proton sometimes in a higher energy level. So we've got energy levels again, but these are inside the nucleus. So instead of having an electron here, we've got a proton. And it sits there, and then spontaneously it will fall back down, and it might go back down to there, and then it might go down to there. And if it does it in 2 steps like that, you'd get out to, well, they're always gamma photons, because the proton itself, so this is E1 HF1, and this is E2 HF2, because you get 2 different ones. So the proton is nearly 2,000 times more massive than the electron, has the same charge, although it's positive. But when it changes energy levels, the energy that's changing is much, much bigger, because we've got a much, much bigger mass. So all of these photons that come out from within the nucleus, they are all of them gamma radiation. Okay, and so it's a metastable state then. Is where the proton has been formed. It's now sitting in a higher energy level, and when it falls down, normally it spontaneously will do that within a microsecond of being produced. But in this weird metastable state of technetium, it sits in this high energy level where for some reason for a long time, so long that its half-life is hours and hours, 6 hours ish. And so it's called a metastable state, because it's not properly stable. It does decay, but it's much more stable than a normal gamma emission. Normally, you would get alpha or beta emission, and then you would get immediately, if it was going to happen, a gamma ray come out, because the proton would immediately collapse from wherever it was into the ground state. And so you would get gamma emission pretty much with either the alpha or the beta. So and so that's the normal way of things. But this particular isotope, and it only happens for technetium, the proton sits in this high energy level for hours, and then it decays. So, and it has this half-life of about 6 hours. So, and in that time, you can purify it, and you can effectively have a pure gamma radiator.
A PET scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in the complete annihilation of both particles, releasing 2 photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
Scanner. Okay, so PET is a positron emission tomography, and there's that word again. So basically, you've got positrons being emitted by this beta plus emitter, this fluorine 18 thing. So F18 is a positron or a beta plus emitter. Okay, and that is emitted from the person. Okay, so what happens is that here is the person, and let's suppose that this is their spine. Okay, and maybe they've got a rib or two, right? And the bone has absorbed this fluorine 18 and is now decaying. It's now decaying. Okay, and what happens is that the fluorine 18 produces a beta plus. Beta plus is antimatter. Yes, antimatter. And what happens is that basically there is so much matter in a person, there's almost no antimatter nearly all of the time. The beta plus particle meets an electron and you're swimming with them, so you can't help but have it meet an electron almost immediately. And what happens is that the beta plus, or the positron, annihilates with the electron, and a pair of gamma photons are produced. And it has to be a pair because of conservation of momentum. So this has to happen inside this sort of donut thing. And you end up, they've got detectors. And so what happens is, there are detectors all round, basically. You might have, for example, let me change colour. An emission from here, say, and because the gamma photons go in opposite directions, one will go this way and one will go exactly the opposite direction. And so this gamma detector or camera lights up, and so does this one. But can you see that the time it takes is going to be different? The arrival time will be different. And that's because it's got to go through much more of the person, and it's got further to go to get to this one. And then you'll get another emission from another bit of bone, I don't know, say there, and that one will produce gamma photons that go like that, and it will, and again, the arrival time is different, and the arrival times are recorded, and you use the computer to build up a picture of where the bones are. So you can get a really, really clear scan. It does take time. And of course, you are exposed to ionizing radiation to do this. And obviously, nobody chooses to do it if they don't have to, because of the ionizing radiation and the fact that it's incredibly expensive. But it does give you one of the only ways of getting a really good bone scan. So this is a PET scanner, and you can see that you're combining you're combining a beta plus emitter with electron positron annihilation, and basically gamma cameras on opposite sides, and you're using the time of flight, the time difference, the arrival time. I'm going to put arrival time difference to build up a picture, so a computer is used to generate an image. Okay, so that's a PET scan. Yeah, and there it is. There's the one that I was going to talk to you about. This is fluorine 18. So this is the isotope that is used to produce positrons in the positron emission tomography machine, a PET scanner. So fluorine 18 emits positrons. A patient is injected with a radiopharmaceutical containing fluorine 18. So they're injected with fluorine 18, basically. It says, describe how a PET scanner is used to locate an area of increased activity within the patient. So if the fluorine gets collected together in one particular place, what will happen? Well, it will decay. It will produce beta plus particles, right? So we need to say this. This is describe. So describe is say what you would see, if you could see such a thing. Okay, so say what you would see. And we need to say at least 4 separate things, and they need to kind of, one of the best ways of scaffolding, arranging your answer for describe questions is to do them in chronological order. I hope you know what that means. So chronological means in the order in which they occurred. Chronos is time, so in time order, basically. So how does a PET scanner work? Okay, so we have fluorine 18 does what? Well, it collects in an organ, perhaps, okay, and decays. When fluorine 18 decays, what happens? Well, fluorine 18 is a beta plus emitter. So beta plus particles are produced. Then what happens? Well, beta plus particles will annihilate with electrons. Okay, so the beta plus annihilate, you have to spell it right, with electrons almost immediately. I can't spell. Immediately they're produced. And annihilation causes two gamma photons to be produced. Okay, 2 gamma photons are produced. Why are 2 produced? They have to be produced to conserve momentum. Okay, so the 2 gamma photons travel in opposite directions. So the gamma photons travel in opposite directions and are detected, okay, at 2 different times. So a PET scanner is a donut machine, and the person lies on a bed there. The gamma photon is produced in there, say, I don't mean gamma, the beta plus particle is produced there. It immediately annihilates and it produces 2 gamma photons. So one of them goes this way and gets detected, and one of them goes this way and gets detected. And can you see that that one's got less distance to go, and consequently it's going to be detected first. I mean, it literally is first. Right, these are things that travel at the speed of light, and they're not going very far. So accurately measuring these times of flight is an incredibly challenging thing to do, but that's how the beastly thing works. Okay, so they're detected at 2 different times, and from those times, from the time difference, the position of the source of the particle can be determined. I'm going to put determined. Okay, can you see that this is describe how a PET scanner can locate an area of increased activity? So all I've done is I've gone through step by step. What happens? What then happens? What then happens? Why that enables you to work out where an area of increased activity. So if we go and have a quick look, so this is, it was exploring, because I did look this up. I did do my homework. I know it's hard to believe it, but I did do my homework. I'm going to go to these ones and look up the mark scheme for this. So, and it was 2017, and it was exploring physics, and it was the last question. Oops, too far. Okay, so let's move that down so you can read it. So question 25A, the patient is surrounded by gamma detectors. I didn't mention that, although I did draw it to explain what's going on. Increased activity where the fluorine 18 accumulates, and then the positrons annihilate. Each annihilation produces 2 gamma photons traveling in opposite directions. The arrival times are used to locate positions. So you can see the 4 points that they are wanting you to use there. So you can see that this is sort of a bit about medical isotopes, but it's also about all sorts of other things in order to get the beastly thing to work. Okay. It was that one, wasn't it? Okay. So has anybody got any questions about that one? Because that one was rather fun. Quite liked that. Okay, so this next bit then, we've got, I'm going to change colour because I can. Let's go, shall we go light blue? Right, so the half-life of fluorine-18 is 110 minutes. Well, I didn't write it down earlier, but it's 110 minutes. Okay, so nearly 2 hours. Okay, so I'm going to write that down. So T1/2 is 110 minutes. It says calculate the time little t in minutes for the activity of the radiopharmaceutical to decrease to 30% of its initial activity. So now we're using the regular radioactive decay equation. So we could do A is equal to A0 e to the minus t over, oh no, it's lambda t, isn't it? Oh. Minus lambda t. T over RC is capacitors. Very similar equation. Okay, so A is activity, A0 is the activity at time is 0. Right, now we want 30%. So A over A0 is equal to 30 over 100, which is 0.3, is equal to e to the minus lambda t. Now, I am going to take logs. I'm going to go to a darker blue so that you can actually see it. So I'm taking logs of natural logarithm of the 0.3, and the natural logarithm of e, it disappears, it becomes minus lambda t. So we want t is equal to log of 0.3 divided by minus lambda. Now, we've got T1/2. We haven't got lambda, so we need to do a different experiment, a different equation to get lambda. So lambda is equal to log 2 over T1/2. If you can't remember it, go look it up on the data sheet. Okay, I am going to do a radical thing. I'm going to leave T1/2 in minutes. And then my lambda is going to be the probability that it will decay in the next minute. And this T will be in minutes. So I'm just going to go with minutes for the whole thing. The equation should work out. If you're worried about doing that sort of thing, then convert it to seconds by all means. So it's just that nothing's squared, there's no difficulty here, so it's fine. So we've got log of 2, oh dear, log of 2 over, and then T1/2 is just 110. Okay, so use my calculator. Log of 2 divided by 110 gives me 6.3 times 10 to the minus 3. This is per minute. Oh dear, I can't do M, can I? That's rubbish. I need to write it like that. Yeah. Going to the minus 1. Right. So now I'm going to put that in here. So I end up with T is equal to log of 0.3 divided by minus 6.3 times 10 to the minus 3. But it ends up positive because log of 0.3 is negative. So we end up with, just plug the numbers in exactly as they are there. Log of 0.3, close your brackets, and then divide it by minus 6.3 times 10 to the minus 3. And this answer will be in minutes. So T is 191 minutes. And the reason I left it in minutes was because they asked you to calculate the time in minutes. This was in minutes. So, so that's how we did that bit. Has anybody got any questions about that? No questions about that. That's good. Right, I'm going to clear my drawings because I've not got enough room now. Clear all my drawings and then let's move this up. So it says PET scanners are not available in all hospitals. This is because fluorine-18 requires expensive on-site particle accelerators, and fluorine-18 has a very short shelf life. Suggests the impact this may have on the treatment and diagnosis of patients in the country. So they want you to say something like the availability is going to be patchy, and it's a bit of a postcode lottery. It depends whether or not you live close enough to a big hospital where they've got one of these accelerators. Fluorine-18, all of the beta plus emitters, they're none of them natural. There are no natural beta plus emitters. They have to be made. So yeah, so that's quite interesting. Right, let's move on. We've got another 5 or 6 minutes, so I can move on to another isotope question. So that's about polonium. It's not a medical isotope one, so let's step through there. Another fluorine-18 one. Okay, so let's try this one. Again, you'll notice that this is question number 25. These are considered really hard questions. So they're the last ones. This is a paper 2, an OCR paper 2. Okay, so the nuclear reaction below shows how the isotope of fluorine is made from the isotope of oxygen. Can you see? They accelerate protons and get them to join with the oxygen. So it's made. It says the oxygen-18 nucleus is stationary, and they've made the stationary bolded, so that's important. The proton has a kinetic energy, and they've given you the kinetic energy. The binding energy, oh, we haven't covered binding energy yet. I think we can't do this one, not until we've got binding energy under your belts. It's next week, I think, binding energy. Tuesday next week. So let's leave that one. We could leave the binding energy bit and just do this bit. The fluorine-18 is a positron emitter. Name a medical imaging technique that uses fluorine-18 and state one benefit. Okay, so fluorine-18 is a positron emitter. So this is used in a PET scanner. Okay, it's positron emission tomography. And I haven't talked about this word, have I? Tomography is layers. So this is taking effectively a picture of a slice of you, and then another one, and then another one, and then another one, and then putting all those slices together to build in a computer a three-dimensional model image, so you can then have a look at it from any angle and so on. So tomography, but the same word comes in a CAT scanner. Sometimes it's a CT scanner. It does a similar thing, but with X-rays, and the C stands for computerized tomography. So this is computerized tomography, and it does it with X-rays. Similar idea though. The machines look very similar. You've got, a donut with in the case of a CAT scanner, an X-ray source and detector whizzing round. In the case of a PET scanner, gamma detectors, gamma cameras all round. So they look similar. Polo machines. They call them polo machines because they look like polos because they're white and they've got a hole in the middle. That's not a proper name. Don't put polo machine into your A-level, okay? I'm going to delete it. Yeah, that's not a proper name. It's just that the people that end up being treated, one of my friends, she was treated and she called it polo machine. Anyway, right. So describe how the components of a computerized axial, oh, that's the A. I missed out the axial. Sometimes they don't put it in, you see. Tomography, CAT scanner can produce high quality images of the internal structures of the patient. So we haven't covered that. I will do that when we do medical physics as the option topic later on in the year. So moving on, and that's the end of that question paper. Right, let's keep going. There's a few more. That's that same question. Right. This is about stability curves. So not medical isotopes. We could come back to that though, because that looks like quite a nice one. This one's about absorption. I hope you recognize that that this thing is the source and this is the detector. So this is like a 𝗥𝗱𝗶𝗶𝗃𝗃 tube. Okay. A 𝗥𝗱𝗶𝗃𝗃 tube detects all different sorts of ionizing radiation, all the different sorts. It's better at some of them than others. So, and that can become significant. Right, so not that one then. Oh, this is carbon dating. Should we do that? We've got a few minutes. Let's do, describe the fundamental particles within an atom of carbon. So the fundamental, proton and neutron are not fundamental. The fundamental ones are the quarks. So you have to, in terms of the hadrons, okay, so be aware. Leptons, the electron, the neutrinos, those are fundamental, but the proton and neutron are not fundamental. It's the quarks that are. Right, so then part B, it says the half-life of the isotope of carbon is 14. It's 5,700 years. So T½ is 5700 years, right? It says show that the decay constant, and they've given it in years to the -1. So remembering that lambda is log 2 over T½ we've got log 2 over 5,700. And if we leave this in years, we'll get our answer in years. So it's log 2 divided by 5700. And we end up with 1.216 times 10 to the -4 years to the -1. So we've done a show that. We've put in all of the different steps. We've lined up our equal signs. We've worked out our answer, and we've given our answer to more significant figures than are given in the question. The fact that they've given this number in the question, though, means that we're probably going to need it in the next bit. So they wanted to make sure that we got it. Okay, the next bit then says carbon dating is a technique used to date an ancient wooden axe. The ratio of carbon-14 to carbon-12 in the axe material is 78%. Right, so carbon dating relies on the fact that cosmic rays from space create carbon-14 in our atmosphere. And we make the assumption when doing carbon dating that the amount of carbon-14 in our atmosphere is consistent. It's constantly being renewed by more cosmic rays from space, which arrive at a constant rate. So the amount of carbon-14 in the atmosphere is constant. And every living thing on Earth basically exchanges carbon with the atmosphere. So plants absorb carbon dioxide from the atmosphere and consequently some carbon-14 that's in the atmosphere. And then animals eat that carbon and turn it into a bit of an animal, and then that animal dies or it decays or something happens, or it's then eaten and it's breathed out and it is returned to the atmosphere. So whenever something's alive, you've got this carbon cycle with the atmosphere, and the carbon goes round and round. And the amount of carbon-14 in that cycle is constant because the half-life is 5,700 years. So nobody lives that long. And so the carbon that's in part of you doesn't have a chance to decay much before it's back recycled in the atmosphere. But as soon as you die, or the tree that the wood was made for the ancient axe dies, then it's no longer exchanging carbon with the atmosphere. And so the amount of carbon-14 decays exponentially. And from how much is left compared to how much there was at the start, you can work out how old it is. That's the principle of carbon dating. So that's what we're going to do. So we've got the ratio. It's got the ratio of carbon-14 to carbon-12 in the axe material. So we've got C14 over C12 in the axe is 78%. So it would have to be multiplied by 100. No. And then the current, it's 78% of the current carbon ratio. Let's write it differently. Let's write this differently. Okay, so the carbon-14 to the carbon-12, and then this is in the axe. Is 78% of the current ratio. So times 0.78, so that's 78% of that is equal to the carbon-14 over carbon-12 for now. So I'm just going to leave that without an extra subscript. Okay, so we've got that this is 78% of that. Okay. So can you see that the carbon-14 itself is 78% of what it would have been? Okay, is now in the axe is now 78% of the carbon-14 at time is 0. Okay, that looks horrible. That's a horrible way of writing it, but I'm going to leave it like that. So we've got to work out the age of the wooden axe. So we can do it from n over n naught is equal to e to the minus lambda t. This is the number of carbon-14 compared to the original number, and we know that it's 0.78. So this is equal to 0.78. It's really much more simple than the way they've described it. That's what we've got to do, and we've got to find t. So we take logs. We always take logs in these ones. So it's log 0.78 is equal to minus lambda t. So t is equal to log 0.78 over minus, and lambda we worked out is there 1.216 times 10 to the minus 4, and we work out. And we get 2043. What are the units? Can you see it's going to be in years because we didn't change it? So this is in years. So it's 2,000 years old, this wooden axe.